Okay, good morning everyone. My name is Will Tarpeh. I'm an assistant professor in chemical engineering, but as you'll see from the work of me and my group, we spend a lot of time thinking about the environment through the context of chemical engineering. Today I wanted to talk a little bit about our work about reimagining wastewater. Most of us think about wastewater as, unsurprisingly, a waste, but I'm here to tell you that it has some use, and to tell you a little bit about the specifics on the molecular level of how we managed to do that. So today I wanted to start by thinking about, kind of as many of us are technologists, we design new technologies, and this old saying, don't miss the forest for the trees, right? Sometimes we can get so excited about our technology, whatever our widget is, that we can miss what the big problem is, right? And so a lot of the work that we do is zooming in and out between the very molecular scale, thinking about changing different forms of nitrogen between each other in wastewater, but all the way to what difference is this going to make in the world? How many greenhouse gas emissions are we going to prevent, right? So we're going to go between system scale assessments, the latter of what I just said, and molecular scale. So to start with that system scale, there's a concept that we think about a lot called the planetary boundaries framework. Has anyone heard of that framework? I see a few nods, yeah. If you're interested, there's actually like a Netflix special about it. So just Google Netflix and planetary boundaries, and there's a cool documentary about it. This concept ties into what the planet can handle, right? There are these different categories: climate change, ocean acidification, these different categories that are these pieces of the pie, right? And it's what can the planet handle in terms of each of those categories. If we're doing well, what the planet can actually handle is within this first circle, right? Within the green area, that means we're within the safe bounds of what the planet can handle. Some of these you can see we're far out and we're far beyond what the planet can handle, and thus this is a measure of sustainability. And so I'm going to talk to you today in some detail about the nitrogen cycle and a little bit about phosphorus, but mainly about nitrogen. But in short, we've far surpassed what the planet can handle in terms of the nitrogen that we emit into the environment. And so what that means is that the planet is constantly trying to catch up with us, right? And so we need to not only stop emitting or reduce our emissions, we need to take care of the emissions that are already in the environment. And so one of the ways that we think about this in my group is resituating waste, right? We can think about one chemical compound, say ammonia, and depending where it is, we consider it a product or we consider it a pollutant, right? Ammonia is a huge portion of the fertilizer that feeds more than half the world, right? Half of us wouldn't be alive without ammonia that's produced via the Haber-Bosch process, right? However, ammonia in wastewater we consider a pollutant. Ammonia hasn't changed anything about itself. It's still nitrogen with 3 hydrogens around it. But it's in a different environment, and so we decide it's a pollutant, it's a waste, or it's a resource. So what that means is that if we resituate it and just change its environment, so to speak, it can be a product instead of a pollutant. So let's talk a little bit about energy and separations, as we call it. But broadly speaking, here's the US energy consumption. This red bar here is industrial energy consumption. Now, when I tell you like chemical manufacturing energy consumption, many of us probably think about running reactions at high temperature or high pressure, right? But in fact, about half of the energy used to make all the chemicals and the products that we use is from something we call separations. It's after you do a reaction, you have to make a high purity product, right? If we're thinking about the pharmaceuticals that many of us take or the clothes, we want a pure product, right? And it takes a lot of energy to separate mixtures and make them pure products. And so this idea of separations, kind of taking a mixture and putting it into pure products, is something we think about a lot. So if many of you have probably heard of reverse osmosis for desalination, that's a separation process. You use pressure to drive water through a membrane. Similarly, if we think about the clean energy transition, one of the kind of underbellies of that is that we are close to running out of critical minerals, right, to be able to make the batteries and many other things that we need. And so we need to separate lithium from other elements. And then we can also soften water, which means removing calcium and magnesium. So if we think about this spectrum of all the separation techniques we have, in general, we spend most of our money and time developing high energy ways to separate elements from one another. We boil water through distillation, or we boil things through distillation. What we're trying to do as a field is moving towards these low energy methods of doing the same thing, right? How can we spend less energy and therefore spend fewer greenhouse gas emissions to achieve the same high purity processes that we're all used to? So I told you we'd talk a little bit about wastewater. Here's kind of a map of wastewater in one graph. So each of these pies that you see here is a different type of wastewater. The one you're probably most familiar with is municipal wastewater. That's like when we flush our toilets, we take showers, and it goes down to your local treatment plant. That's the wastewater of interest. But there's a few things we can think about for any different wastewater. The first on the x-axis is the global flow rate, how much of that wastewater there is. Okay? On the y-axis here is the total dissolved solids, how much stuff there is dissolved in there, right? How salty is the water. And so you can see we can just kind of look at the corners here and say some of these waters are very high in volume, but they're quite dilute, versus these waters, like lithium-ion battery leachate or produced water from oil and gas, these are very low volume, but very concentrated, right? So that's two facts, the global production rate and how concentrated the wastewater is. And then we can look at the value of the wastewater in billions of US dollars. So this is basically what we're flushing into the environment. The bigger the pie, the bigger the value. Okay, so something like municipal wastewater, that's on the order of $30 billion around the world that we're just getting rid of and we're treating as a pollutant. Then finally, the fourth thing about these wastewaters is all of the different elements that are in them. This is what we mean by wastewater as a modern mine. These are all the chemicals that you can pull out of a wastewater if you had a way to purify one element from another. And so what we spend a lot of time doing is designing processes that can literally produce highly pure inorganic nitrogen, for example, ammonia, from very complex wastewaters. We call this project, broadly speaking, wastewater refining. We use that term refining on purpose. When I say refining, you may think about oil and gas refining. Great, that's what I want you to think about. But we're going to do it a little differently. But if we zoom out of what refining means, it means you take a crude feedstock of some sort, you have dozens of processes that turn that crude feedstock into dozens of useful products, right? Plastics, fuels, etc. Let's think about the same thing, but for wastewater. We bring in one of these wastewaters, we design all of these different unit processes that will allow us to produce many, many high purity products, right? So that's what we're after here. So how do we go about doing that? We're going to do this by tuning different processes, many electrochemically driven, to be able to produce many different nitrogen-containing species or lithium-containing species. And here's the zoom in that I was talking about. So these are the unit processes we're developing. We want to know what's happening at the molecular scale, but also think about what is the impact that these are going to have on the environment. So let's dig in a little bit to the lithium case. And I mentioned this a little bit already, but we can, in short, think about how much lithium we have and how much lithium we need, right? And so this lithium carbonate equivalent is just how we measure lithium. Here's the next decade or so. It ends in 2030. And you can see that these lines here are the demand for lithium, and these curves here are the supply of lithium. In short, the demand is going to be greater than the supply, especially over the next several years. And so together, our lithium carbonate equivalent supply is on the order of 0.5 megaton per year or so. But our gap is more like almost 2 megatons per year. And what's happening is that we're letting a lot of this lithium into the environment, but we don't have enough to make, for example, all of the batteries that we need. Interestingly, though, if you look at what's in this wastewater, we have enough lithium in 2 major wastewaters to match this shortage, right? So if we look at oil and gas brines, there's a lot of lithium there to recover. And then if we also look at spent lithium-ion batteries, right? After our batteries and our electric cars die, so to speak, or they reach end of life, we can get the lithium back from them, right? And that makes a lot of sense. And not just the lithium, but the nickel, the cobalt, the manganese, etc. And so what we do as a lab in the lithium space is we design membranes, which are selective barriers, that allow us to select just the lithium out of a mixture. So say you take a battery, you put it in acid, because that's what you normally do to get rid of a battery or to dispose of a battery, and then you have this mixture of a whole bunch of different metals. And what we want to do is say, I'm going to see these different metals and just pick out the lithium ions somehow. So that means I need to be able to tell the difference between a lithium ion and a cobalt ion, or a lithium ion and a nickel ion. There are different things we can use there. We can use their size, we can use their charge, right? But eventually what we end up having to use is actually chemical selectivity. We need molecules that bind with lithium, but will not bind with nickel or cobalt. And that's really the frontier of where we're at. Now, interestingly, these membranes can be applied throughout the battery life cycle. So what I just described here was like lithium going through, but other cations like nickel or cobalt not being able to go through. We can use this to actually make the raw materials for batteries. So from some of these brines, we can get lithium to go through a membrane, but leave sodium and magnesium behind. And even in batteries, we can get lithium to go through an electrolyte, but not let competing ions through, like polysulfides. And so this idea of membrane separations, if you remember from that spectrum of separations, membranes are really low energy. And what we're going to do with all of these charged electrodes is do electrodialysis, right? We're going to attract these positive ions to this negatively charged electrode and select for lithium in a competitive way. Okay, so that's the case for lithium, but the case for nitrogen here is that we have this nitrogen cycle, like I mentioned on the first slide. We have all these different forms of nitrogen that we call reactive nitrogen versus inert nitrogen in the air that we breathe. But what humans have done to this nitrogen cycle, is we've skewed it towards reactive nitrogen. So basically, we have a net discharge of nitrate ammonium into the environment. Many of you have probably heard of N2O, a very powerful greenhouse gas that's 300 times as potent as CO2. And so we're able to remove some nutrients from wastewater, like nitrogen, from wastewater treatment plants, but you can see we don't remove as much as we introduce. So what this means is we're just discharging a whole bunch of nitrogen into the environment. And as a lab, what we think about is let's take those pollutants and turn them into products, but high purity ones. And so a little more about this background, and I'm focusing on the background so you can kind of see the motivation of our work. What this leads to, this nitrogen discharge, is these harmful algal blooms that you can literally see from space. You may have heard of like the dead zone in the Gulf of Mexico, for example. It's the size of New Jersey, okay? That the oxygen is overconsumed in the Gulf of Mexico, an area the size of New Jersey. And our plan for that is we don't really have one. We just wait until the water turns over. Right? And that's all the nitrogen that's coming from the Mississippi, all throughout the US, from much of our croplands, and it ends up in the Gulf of Mexico. So what we're attempting to do is remove that nitrogen and recover it before it ever gets to the Gulf. Whenever we produce ammonia, we also produce a lot of CO2 as well. And then there's also the equity challenges here. So ammonia is produced at Haber-Bosch facilities, and that's a process that turns N2, nitrogen gas, into ammonia. But there are fewer than 100 of those around the world, which is not a bad thing, but it just means that everyone doesn't live the same distance from a fertilizer production plant, right? Someone in sub-Saharan Africa or someone in South America lives very far from one of these black dots. That's a Haber-Bosch facility. So what does that mean? They end up paying a lot more, even though their income may be a lot less. And it means we all pay the cost of transporting ammonia very long distances. So what we think about is, can we produce this ammonia on site, right? And the cool thing about wastewater is that wherever there are people, there's wastewater. So we don't have to travel long distances to get our ammonia. We can just recover it on site. So one of the examples of how we do that is a process that we call electrochemical stripping. And it's a selective process that allows us to really take any wastewater and recover just ammonia from it in a high purity solution that is ready to be used as a fertilizer. So here we have an anode that's titanium based and a cathode that's just stainless steel. We pass electricity between these electrodes, and we feed in some wastewater, like think of the pie charts I showed you on an earlier slide. So ammonia comes into this anode chamber. We have a dilute salt solution sitting here in the cathode, and sulfuric acid sitting in the trap that's going to allow us to produce ammonium sulfate. This anode chamber will acidify due to a reaction called oxygen evolution, but what's important here is that we're producing protons that will make the pH of this chamber go way down. So as we do that, ammonia will turn into ammonium, NH4+, and because we have electrons moving through this external circuit, there's an impetus for positive charges to move as well, to conserve electroneutrality. So positive charges will move through this membrane that we select for ions that have a positive charge. So that's our first separation based on charge. And so this ammonium is not the only cation in wastewater. There are other ions like sodium, magnesium, calcium, etc. So our separation isn't quite complete yet. We need another step. In this cathode chamber, we'll do hydrogen evolution. So this is just water electrolysis or water splitting, to introduce terms you may be familiar with. And when we make a whole bunch of base here, we're going to take the proton off of this ammonium, NH4+, and make ammonia, NH3. And ammonia is our product, right? That's a key product that is used to make fertilizer. We will strip this ammonia out of solution because it forms a gas, and so we're selecting for ammonia based on its volatility. This ammonia will then get trapped in an acid trap chamber, and we've made ammonium sulfate, which is it's like the second most common liquid fertilizer around the world. But ammonium is the only thing that passes both the charge test and the volatility test, right? So a way to look at this more clearly is to look at some of the data from this operation, right? So if we're looking at time here and the mass of nitrogen in these different chambers, you can see our nitrogen leaves that first chamber. It goes through our middle chamber in black, and it ends up in the rightmost chamber that I showed you, the trap chamber. And how much of that nitrogen ends up there? To the tune of around 90%. And these are different real wastewaters that we've tried this on. So when I say we can take really any real wastewater, feed it into this chamber, this first chamber, and produce a high purity ammonia product, that's what I mean here. What I'm not showing you is all the selectivity data to show you that ammonia is the only thing that goes through, but you'll just have to believe me for now, I suppose. Okay, so being at Stanford, we're surely excited about this, this innovation, but it's not enough to just say, cool, I made a new process, I hope it works and I hope someone adopts it, right? And so then what we asked ourselves over several years is, how do we translate this from the lab into practice? And one of the ways, if you were looking really carefully at the time axis, you saw that we did this for one day, 24 hours, which is impressive and challenging, but is not something that someone is going to be investing in. Because it turns out people produce wastewater for more than a day, right? And so one of the things I challenge one of my really excellent students, Anna, to do is say, I want us to run these 2 reactors here. Here are the 2 reactors. I want us to run them for as long as possible until they fail. Okay? As long as possible ended up being a little more than a month, 35, 40 days, but these 2 reactors were side by side and we were running real urine through them nonstop, okay? On the order of a few liters per day. And so what we found here was that the process works pretty well, but some of the failures arise from when the membranes fail, but we can replace them and we can produce this high purity product continuously for 35, 37 days. And this was kind of a huge deal because we were able to advance the work beyond just the lab. Here's one of my students, Arisa. You may recognize this. Arisa's a mechanical engineer, so this is actually a mechanical engineering building. But Arisa said, Will, this is great, but how are you going to power this, right? You'd need a big battery to do it. Why not use a solar panel? So she took, you'll recognize the same reactor, and put it outside, right? And ran it throughout the day and actually throughout the night as well, so that we could see a decentralized on-site manufacturing as well. And Kindle, one of my postdocs, has now taken this and tried to scale it up at the Kodaga Resource Recovery Plant. I don't know if you guys are familiar with that, but it's a wastewater treatment plant on campus. It's a pilot scale one where we can try out new technologies. And so this is how we're trying to scale this out of lab and get to actual demonstration. So some takeaways as the last slide here. Hopefully you got the idea about how we're scaling between very molecular scale for the chemists among us, but all the way up to how do we get this into practice. And we believe that these integrated multi-scale investigations are a key way to accelerate implementation. These arrows have to go both ways if we're going to advance our work outside of the lab and into practice to make the differences we hope. And finally, this wastewater refining really requires multi-scale solutions from selective membranes all the way up to huge electrolyzers. So with that, I'd love to thank my group and happy to answer any of your questions. Thank you.